Hello students, welcome back for the next episode of Physics Marathon class, and again we are here to discuss the one more section of your AIATS Plus mock test 4, and that happened on 9th of February. So let's understand few more concepts with the help of these questions you have experienced in your mock test. So what prime areas we will be covering in this particular session of your physics marathon, and this is system of particles and rotational motion. So this is the first topic. Then we'll have moving charges and magnetism. So that is another area we'll be targeting. Then electromagnetic induction, that EMI would also be there. Dual nature of radiation and matter, that is also one of the chapters we'll be dealing with. Then thermal properties of matter. So these prime topics will be covering in this particular session of this physics marathon class, and myself Puneet Kathuria, your physics faculty at Aakash. So let's understand few concepts based on these topics. Now first, your question says, what are the coordinates of center of mass of a point mass of 2 kg with coordinates 2, 3? This is quite an interesting situation. So what is this center of mass is? So first of all, I am writing this center of mass as yes. So I am writing center of mass primarily as COM. So COM stands for center of mass. So center of mass, particularly, it is defined as point where whole mass of the system is supposed to be concentrated. So this is the standardized definition we have been observing in most of the concepts of physics, in most of the books, different books. So important concept is point. So it's not a mass. What is important about center of mass is a point. It's a coordinate point. It's coordinate point in space, and it is always defined for system. System comprises of point masses. So system is defined for point masses. So point mass is something so this is basically a relative concept. So point mass itself, it is such a small size particle as compared to the distance of observation. So point mass itself represents center of mass. So point mass is basically center of mass for that point mass. So point mass represents center of mass itself. So it is not defined for point mass, because point mass is a mass which is very, very small in size, restricted to a point only, and so the definition of center of mass clearly says it's a point. So for a point mass, center of mass coincides with the same point. So your question is very same. So you have a point mass, coordinates are 2, 3. So for this, coordinates means this is This is the location or position of your point mass. So that position itself represents the same. So its center of mass for a point mass lies at the same position 2, 3. Now one more important concept is system. It means it is defined for system of particles. So for a point mass, point itself represents the center of mass for that point mass. But what do you mean by system? So it means center of mass is defined for a system of point masses. And you know, when you say it is defined for a system of point masses, it means defined for minimum 2 particle or 2 point mass system. You got it or not? So it means it is defined for minimum 2 particle system, and these 2 particles are again your point masses only. So if I elaborate it further, so let's suppose to define the position of 2 particles, we'll take one coordinate system x and y. So let's suppose this is particle M1. Its position vector is R1 only. And if I say position vector, so its coordinates are x1, y1. That we understand it. So consider another point mass M2 and its position vector is R2 only. So it means if I write down the coordinates as x2, y2. So it means if I ask you the center of mass for this particle M1, so that itself is x1, y1, and for independently for point mass M2, that is x2, y2. But as we have just said, it is defined for system, and system means more than 1 point mass. So minimum you should have 2 point masses. So what is important is for 2 particle system, center of mass is defined. So there are important points to be noted for this 2 particle system. So let's suppose the center of mass for this particle system, 2 particle system, lies somewhere here. So important point is center of mass for these 2 particles, these 2 point masses lie on the line joining the center of these 2 point masses. That is important. Between these 2 point masses, that is second important one. And if I ask you the position vector of this center of mass, so position vector for center of mass for 2 particle system is also given by this formula. So do we understand? So this is 2 particle system and center of mass is defined for minimum 2 particle system. So this point where the whole mass of the body or this system is supposed to be concentrated, this center of mass also has coordinates x and y. So what is your x coordinate for center of mass? So that would be given by m1 x1 m2 x2 by m1 plus m2, and similarly the y coordinate can also be given by this formula. So this is the position or the coordinates for your center of mass for minimum 2 particle system. So this is all about this one, and what we have just understood is one important point, center of mass is a point in space. So it represents point, not a mass. Second thing, it is defined for system of particles. And to define your system, you should have minimum 2 particles, these 2 point masses. If they are placed together, so they can represent one system. And minimum for 2 point system, we have just written down the formula for the position of the center of mass and coordinates of the center of mass. Any doubt from this part? Any doubt? So, shall we move? If you have any doubt, you can please ask your question, or we should move on. Shall we? Fine. So, I am moving ahead. Now, the next important area what we will be dealing in this question is, the question says a body of mass m, small m, is rotating with angular velocity 10 radians per second. If rotational kinetic energy of body is 100 joules, then moment of inertia of the body about the same axis of rotation is. So this is again from your system of particles. So moment of inertia, we write it down as I. And in general concept, if I give you moment of inertia, that is mk square. So it means m is the mass of the system, k is the radius of gyration about, that is radius of gyration is the perpendicular distance from the axis of rotation. So this is moment of inertia, and this moment of inertia is we need to calculate. So this is what we have to find it out. But what question says, if rotational kinetic energy, so your rotational kinetic energy this is given to you, or this is known to us, that is we can write it down as half I omega square. Students, last time I have been suggesting you, last time also I suggested you this thing. If you really want to excel in your NEET 2025, I would rather suggest you, I would rather recommend you if you can memorize as many formulas as you can. Because if you know the formula, then it means you can easily solve the numerical. So this is the concept. So what your question says, rotational kinetic energy is given to us as 100 joules. I, we need to find it out, and omega, that is given to us as 10 radians. So 10 square means 100. So this 100 goes with this, and I comes out to be 2. If you look at this, the unit wise m stand for kg, k square radius of gyration square, so this is standardized meter. So I we can write down as 2 kg meter square. So we have to pick the answer. Yes, this is the one. Now this is very, very important. We have just understood this concept, the rotational kinetic energy. I would like to add on one more concept based on the same. I'll just simply add on your work energy theorem. It says, this is something additional, I am giving it to you. Work done, we can write it down as change in rotational kinetic energy. So half I omega final square, that is the rotational kinetic energy, minus half I omega initial square. So this is the change in rotational kinetic energy. So this is work done. So this is one more area which is equally important. Why we are dealing all these, why I am giving you all these extra stuff? Because your time permits me, because this is not to deal just with the numericals, just to deal with the surrounding concepts which are equally important and close to your NEET. So if I'm like these areas, if I can help you to understand these more areas or new concepts within the given time frame, so I feel myself lucky कि I am able to give you all these extra concepts. One more extra concept that I would like to give you on this part is your relation between angular momentum and rotational kinetic energy. If I give you the way to remember this, I am giving you one analogous relation that is there in the translational motion. So if I give you the reference of your translational concept, so we know kinetic energy is given to you as half mv square, and if I multiply this with mass, so that becomes, and divide it simply again by mass, so that gives me p square by 2m as the relation between the translational kinetic energy and the linear momentum. And to maintain the same formula in rotational motion, we simply say rotational kinetic energy can also be written as, so what best we can understand is you replace this p stand for linear momentum, replace it with your angular momentum. So angular momentum we write down as L square, we write down p as L, so p square becomes L square, and finally 2m, and m we can replace it with I. We know moment of inertia plays the same role in rotational motion what mass does it in translational motion. So this is how we have got another concept, another relation, and that is a relation between rotational kinetic energy and the angular momentum. So we can simply write down rotational kinetic energy as L square by 2I. Any doubt? Any doubt? So sir, please also tell translational energy. Translational energy we simply write down as half mv square, that is the translational kinetic energy we are dealing here. So any doubt from this part? If you have any query or any doubt that is coming to your mind, you can still confirm it, you can still clear your doubt, or shall we move? Please allow me to move further then. So let's move. Yes. So now we are coming to the new concept. This is our third question. Again, I would like to highlight, this is regarding your AIATS Plus series. AIATS Plus. AIATS is again a well-known series that we have been doing it since last almost so many years. That is the benchmark or for this Aakash. But what does this plus stands for? Plus is basically personalized learning for ultimate success. And this is something really in demand, and on this demand we are bringing some of the important areas. So these all are the questions which are probably very important for your NEET, and we are teaching you the concepts surrounding these questions so that you can attempt not only these kind of questions but the questions related to all these areas which are close to these concepts which have been asked in these questions. So, shall we? Yes, I think we should. Now, next question says average EMF induced in a coil in which the current changes from 2 ampere to 4 ampere in 0.05 seconds is 8 volts. The self inductance of the coil is. Again, this is quite easy and interesting case. What is best is, again, if you know the formula, then you can attempt it like this. So, formula game is very important. So, as per your Faraday's law, induced EMF is given to you as rate of change of flux with respect to time. And here we are talking about the magnitude. So, magnitude means will not consider the negative sign which is there. So, this is d phi by dt, and we know in case of inductor your flux is given by Li. So, your induced formula, induced EMF becomes L being constant. So, this is L di by dt. So, this is important formula. Again, I am highlighting one more area, that means if you know the formula, you can solve it like this. So, please from today onwards, please write down your formula chart, make a list of all the formulas, and that would help you to solve all the numericals in the shortest, quickest possible way. So, what this question says, once we know the formula, we are aware of it, let us apply the formula. So, average induced EMF we are talking about. So, induced EMF is 8 volts. The self inductance of the coil, so we need to find out L, but current changes from, so what is the final value of current? 4 ampere and initial was 2 ampere by time, and time is 0.05 seconds. So, 8 into 0.05 by 2, and that is L. And when you solve it, so what you will end up with? You will end up with, this is 0.4 by 2, so that means 0.2. What is the standard SI unit for self-inductance? We know it is Henry, and we write it as what? We write it as capital H. So, 0.2 H is the answer for this situation, and this is a correct option. So, this is 0.2 H, H stand for Henry. Now, instead of self-induction, let us suppose if I give you a pair of coils. Pair of coil means, I am hinting you, pair of coil means one is primary, the other one would be secondary. So, I am talking about the mutual inductance. So, if you have mutual induction, so in case of mutual induction, you have two coils, primary coil and secondary coil. The formula for the average induced EMF would be parallelly written as, instead of L di by dt, we will be writing it as M di by dt, where M is what? M is coefficient of mutual induction. So, this is coefficient of mutual induction, and the best part is for the SI unit for this would again be Henry, and that you will be writing it as H only again. So, this is Henry in case of mutual induction. So, these are the two parallel concepts, and any doubt from this section? If you have any doubt, you can please confirm it. You can ask me any doubt if you have. So there is one question coming up. What is the formula for L in terms of I? So let's build up. So consider a coil. So current I is passing through this coil. So N is the total number of turns we have, and let's suppose L is the length of the coil we have. So first you need to find out flux. We know as current is passing through this, so there would definitely be magnetic field lines within these. So what is the formula for the flux is? So that would be given to you as NBA for this, where N is the total number of turns, B within this. So what is the magnetic field? Mu naught Ni, where this is number density we have, that is total number of turns per unit length. So whereas capital N is this one into area. Do we understand? So this is the formula, and in the previous case, like what you have written for the flux as Li, so you simply equate it with Li, this I goes with this. So what is the value of coefficient of self-inductance? So if I replace this small or this capital N, maybe like using this formula, either you can write down in terms of small l or small n, or you can write down the formula in terms of capital N. So let's write down capital N. So capital N we can write down as N into L mu naught N into A. So it becomes mu naught N square L into A. So that is how you got the formula for, or we can simply write down in terms of this N, we can write down as N by L. So this formula can also be written like this. So that is, now don't get confused, this is coefficient of self-inductance and this is the length. So let's replace this length with small l so that you don't get confused. So I am replacing this capital L with the small l just to avoid this confusion. So this coefficient of self-inductance mu naught capital N square small l into A. So this is, so one of the question asked me about the formula for L in terms of I, or we can write down like this in terms of L. So any doubt, any further doubt? Shall we move? Now, next question is again from a very important area. So what it says, a square shaped coil is of side L, that is 5 centimeter, and 10 turns carrying 2 ampere current. The magnetic moment of this coil will be. Very important, this is magnetic moment. So magnetic moment of coil. We write down magnetic moment as M, and I am writing this M as a vector quantity. So this is the magnetic moment, and the formula is current into area. So this is the simplest formula, and this is for one coil. But if you have n number of turns, so the same magnetic moment can also be written as n times, that is number of turns, current into area. I am writing down this as a vector quantity, and we know direction of this vector is from south to north pole of your magnet. This is important. South to north pole. So this is something really important. Now let's come back to the main numerical first, then we'll try to explore further how we'll define the direction and what is the importance of this direction or area vector, how we'll define it. So first we need to calculate this m, and here I am talking about just the magnitude part, no direction. So a square shaped coil of length 5 centimeter and number of turns. So this n is given to you as 10. This is number of turns. Current is 2 ampere, no doubt. So this is 2 ampere. If I'm not writing down the units, reason being the area A and ampere, so don't get confused. So just to avoid that, I am writing down current as 2 only without units. And what is the area? So area of square, so that means 25 centimeter square, but this area has to be in standard SI unit. So centimeter square, I put it as this one, minus 4 meter square. So if I write down the units, SI unit, so this is ampere. I'm writing ampere completely so that you don't get confused or confused with the notation A that represents your ampere and area. So this is ampere into meter square. So that is the complete unit. So ampere meter square, that option is also there in your answer. So let's do the calculation. So this is what? Do we? So what you'll end up with? Now I am writing ampere as A into meter square. So let's pick the option. So this is the second option. So I hope we have understood this point, how to calculate the numerical value of magnetic moment of the coil. So this is important. Any doubt from this part? Any doubt? Now let's build up one more concept, how to define the direction of this magnetic moment, and we'll restrict the situation to coil only. So consider a circular coil. So you have a circular coil, something like this. I am drawing another coil Y. Reason being, I am considering current in one of the coil as clockwise. So it carries current clockwise, and in another situation I am carrying current counterclockwise or anti-clockwise. So these are the two probable situations we have. Now how you define the magnetic moment of this? So that is important question, and most of the students, they commit maximum errors while defining the direction only, because magnitude wise the magnetic moment is current into area. So if I consider this of radius r, so current into area, so current into area. So look at this. These coils carrying same current I and of same size, but the difference only is in the direction of the current. So magnitude wise, the value of magnetic moment will remain same So difference is only in the direction part. Now this is the coil with counterclockwise. So I would like to highlight. So let's suppose you have a coil like this and current is like this. So when you observe it from this point, from above the plane, so what you observe is, you will observe south pole here and north pole of the magnet here, because current carrying coil behaves like a magnetic dipole. So this will have a distinct north and south pole, and we know magnetic field lines, they are originating from the north pole and following a close path like this. So what is the direction of magnetic moment? We have just stated it is from the south to the north, and if I consider this downward direction as your K, so don't you think it is going inside in the plane? So if I put that K as minus K, so I hope, because we have assumed the coil in XY plane, so magnetic moment would be directed downward inside the plane. So this is, coil is assumed to be in XY plane. Then magnetic moment of this current carrying coil would be perpendicular, and that would be directed downward. How you justify the direction? Magnitude wise, it goes the same in the other situation also, when current is anti-clockwise. So you have a north pole and you have a south pole. So this is something like this. So this would be plus K cap. So when I am writing with the direction, so I'll simply put it as the vector quantity. So this is something which is important. If you have current carrying coil, that coil would behave like a magnetic dipole. So it will have clear distinctive north and south pole. And how you define the direction of the magnetic moment, that we have just understood how to define the direction with the help of these two examples. Any doubt? So there is one student, Jayant Kajla, who is asking what marks in AIATS is good. When you consider marks, so marks is basically a relative concept. What is important is marks with rank. So what is important is your ranking also. So where you have been placed in your that particular exam, that is also equally important in addition to your marks. So anything, and I am the one who is always asking for 720 from all of my students. So if you ask me what is the best score for AIATS, so I am replying on that. It's not just AIATS, I am targeting for NEET. So anything less than 720 is not acceptable if you have the potential or if you are really wish to score. So always try to hit the bullseye with 720 dot. So that is my target is for AIATS as well as for NEET also. So I think, so there is one student who is asking, sir, once again how you choose signs. So the sign is always defined by the direction of magnetic moment, and that is always directed from south to north. That is the direction of the magnetic moment. And in this situation, south is above the plane of the coil, north is there, so magnetic moment is going down. So that is what you are defining it as minus K cap, because in our situation we have assumed the coil to be in XY plane, and for anti-clockwise it is the other way. I hope you have got the answer. Shall we move? Fine. Lenz's law is based on, Lenz's law is very important, and we have good conceptual cases, numericals, every numerical or concept or the direction of induced EMF or induced current that is being defined by this law. So Lenz's law is based on. So let's understand, let's build up the concept. So if I consider this as your coil and a situation where you have a magnet. So in this experiment, your coil is assumed to be fixed and this magnet is in motion. And let's suppose in one situation it is going towards and probably with the north pole facing the coil. So this is the situation. So now first of all, try to understand what happens if you bring this magnet close to your coil. This magnet is coming close to the coil. So if I draw it like this, so initially magnet is supposed to be here and then here or then whatever it is. So this is how you define. Got it? But when it is relatively closer, see the number of lines passing through this coil or the flux linked with the coil increases. So when it is coming closer to the coil in this particular situation, so because of that, flux linked with the coil also changes, and your Faraday has clearly stated whenever flux linked with the coil changes, it means EMF will be induced in the coil. So induced EMF would also be there, and the magnitude of induced EMF is given by rate of change of flux with respect to time. But it is the Lenz who actually brought the concept of direction. Lenz clearly says the direction of induced EMF is such that it always opposes the cause producing the change of the flux. So first you try to understand what is the main reason for the change of the flux, and the main reason for the change of the flux is the motion of the magnet. Coil is assumed to be a fixed one. So it means it will try to oppose the motion of the magnet. So when you have induced EMF or induced current in the coil, that current will also produce its own magnetic field. So because of that, here we have the induced north pole. So this induced north pole will definitely oppose the other north pole, but you are still bringing it close. So when you are bringing it against the repulsive force, what you are doing? You are doing some external work. It is this work done that gets converted to what? That gets converted to energy in the coil. So this mechanical energy gets converted to the electrical energy in the coil, and we know energy can neither be created nor be destroyed, but it can be just transferred from one form, mechanical form, to electrical form in the coil, and it is purely in accordance with energy conservation. So this is very important, how this law is related to your energy conservation. So this law is in accordance with energy conservation rule. So whatever work we are doing against this force of repulsion, that would help to define this mechanical energy into the electrical energy of the coil. Consider a situation when now magnet is moving away. So when magnet is moving away, it means again the direction of induced EMF is such that it will try to oppose the cause for the change of the flux, and now this time the cause for the change of the flux is motion of the magnet away from the coil. It means here now we'll have a induced south pole, and this south pole will not allow the magnet to move away from the coil. It means whatever work you are doing against the force of attraction, and that is visible to you as energy in the coil. So I hope you have understood it very well. Still, if you have any doubt, because this is very important area, I must say most of the conceptual cases from this chapter and most of the numericals, they are being asked from this Lenz's conservation rule. And if you understand this rule, it means you can answer. There is only one rule, in the whole of the unit, whole of the chapter, that is revolving around is your Lenz's law. So I hope this law is clear to you. Shall we move? Fine. So I'm moving ahead. In the figure shown, a semicircular wire is placed in a uniform magnetic field directed towards right. The magnetic force on it. This is again important. So first of all, the magnetic force on a current carrying wire, I'm writing down in terms of its cross product. IL cross B. You got it? So, or if I expand it, I can write down as BIL sine theta. This is important. This is important. Now, what this theta is? This is the angle between magnetic field and this length, or this is current carrying wire. Look at this. If I consider this one and look at this one, so this is IDL and this is B. What angle can you observe it in this? This angle is 0 degree, and we know sine 0 is 0. So definitely force would be 0. So this is the simplest situation. No need to get into this other details. But now I am framing one more question. Keeping the same, but instead of taking B, let's suppose for the same wire, if I consider my B is something which is inside the plane, so I am writing B vector. So if I consider this both to be as your XY plane and B is going inside, so this is minus K cap. Got it? And current carrying semicircular wire is there. Now, how you find it out? So this is exactly, if I consider a small element and if I define a small force on it, so that I can write down as IDL cross B. So this is important. And for the total one, I need to integrate this, and important is the integration of DL element. This is basically the effective length of the conductor. So this is important. So what is the effective length? You can see. So I can replace this conductor with this rod, and its effective length would be 2R. It's carrying current like this. Got it or not? So effective length in this situation would be 2R. And if I define the force, so look at this, force would be I into, what is the effective length? Effective length is 2R into B. This is the magnitude part. But how you define the direction, that is also important. Just pay attention. For that, I would like to highlight your cross product rule. What is the direction of I? So I is that is along the length. So shall I say this is along x-axis, so that is I. So ideal is I cap. Cross product with B, and B is assumed to be in minus K. You got it or not? So what is this? We know I cross K is minus J, but with this minus K, so this is equal to J, and the direction of force would be like this in this situation. So this is J, and this is the complete answer for this force in vector notation. That defines the direction also. Important, one more area. Let's suppose for the same situation, if I consider a loop, right, and if I ask you the force on this current carrying loop. So force, now we have just understood this dl part, this length, this is basically the effective length, and for the closed path, for the closed loop, this effective length would be 0. So for the current carrying loop, force would always be 0, irrespective of the shape. Had it been a square, had it been a triangle, had it been a rectangle, or this is what we have assumed it as a circle, circular ring, the force would be 0 if it is placed in a uniform magnetic field as per this concept. So I think we have achieved very good understanding of the same concept. Shall we move? Yes, the stopping potential V0 for an experiment of photoelectric effect from a metal surface is plotted with the frequency nu of incident light as shown in the figure. First, we need to understand how we got the graph between the stopping potential and the frequency. So let's write down Einstein's photoelectric equation. And it says h nu is equal to, this is work function, I am writing work function as phi naught plus kinetic energy, and for the kinetic energy I can write down as E times stopping potential. So let's rearrange it. So your V0 is and when you compare it with y is equal to mx plus c, so it is basically in accordance with the straight line equation, and this is how we got the graph. So look at this, this is the intercept, and this is equal to what? Minus phi naught by E. So can you see the slope is equal to h by E. Slope is m, that we can write down as h by E. So this is how we have got this graph. Now Planck's constant. So question is demanding how you define the Planck's constant. So I think we have already achieved that answer. So Planck's constant is slope times E. So slope of the line divided by the charge? No. Slope of the line multiplied by the charge on an electron? Yes. This is a clear winner in one shot. The other, let's understand, intercept cut by the line on the y-axis? No, that is minus phi naught by E. Product of intercept on y-axis in charge. So this is also wrong. So what is the correct option for this is? Planck's constant is slopes time charge. So we have last question of this particular session of this physics marathon. A steel rod has a magnetic moment and a length L. If it is bent into a semicircular arc, then its magnetic moment. This is again important. Now this time we are defining magnetic moment, and this is like of a bar magnet. So earlier we had magnetic moment of the coil. I would like to highlight the basic difference is the formula part only. So magnetic moment of the bar magnet. So if I consider a bar magnet maybe of length L and its pole strength. So pole strength I am writing it with small m, and that represents the pole strength maybe as north pole or south pole. So this is m times L. Unit wise we have defined it as ampere into meter square. So that is the SI unit. We have already noted it down in the previous case also. So unit wise it remains same. Direction wise also it remains same. So let's suppose if I call this end as north pole and this end as south pole, then direction of magnetic moment would still be from north to south. So these two parameters are same. Where it is different for a bar magnet is in the formula part, pole strength into length only. Now I am giving you a wire of length L, pole strength m, length L. So its magnetic moment as per this formula is m into L. L is capital L, so we can write down as capital L also, that is. Now it is bent into the same L is bent into a semicircular arc. I call this radius as R. So length is bent into semicircular arc. So L length can also be interpreted as pi r, that is half of the circumference. Now this is how the poles are separated. So the new magnetic moment I am writing it as m prime. So that means it's m into how these two poles, how this dipole, what is the dipole length, how these two poles are separated. So this is 2r, because we have to pick the answer in terms of capital M. So shall I replace capital R with L by pi, and we know m into small m into L, that is capital M by pi. So the new magnetic moment would be 2m by pi. So 2m by pi. So this is the answer for this. So kids, this is all from today's part. Any doubt you can still ask. So this is again Puneet Kathuria, Aakash faculty, and I am here to understand these concepts and to help you understand these concepts. So if you have any doubt, you can still ask me. Till then, I think I should say goodbye to you. Have a good day and have a nice day. Thank you. Thank you, students.